Welcome to week 7 of remote learning. This week our topic is matrices, which is something that students often see on the ACT and possibly SAT, but it's not something that currently has been in the pre-cal curriculum. We do have new standards coming out next year, and it will be a part of pre-cal and other 4th level math courses. And so since you guys are missing that, I thought it was important to include it this year. So your homework for this week, there'll be some practice problems out of your textbook from section 7.2 and 7.3. And then you will have an 8-question matrices quiz in Canvas. Due to the Memorial Day holiday on Monday, my office hours this week are just Tuesday through Friday from 1 to 2. Also a reminder, any of you that are completing work either to increase your S1 grade or improve your Q3 grade, the deadline for all of this work is Friday, May 29th at 5 p.m. And that is a non-negotiable deadline because that gives me Monday to finish all my grades up and to submit them. And again, make sure that you're aware of your Q3 grade, and if you wanted me to include any of your remote learning scores to try to improve that grade, please make sure that you email me. So 7.2 is called matrix algebra, and in your textbook, those page numbers are pages 577 through 87. So it's a pretty big chunk in your textbook, but most of this material is pretty easy. But again, if you're not sure about something, feel free to use your textbook as a reference. So first of all, we just need to define what a matrix is. Again, some of you may already be familiar with this. To me, the simplest way to think of a matrix is just a way to arrange data. If you think about my grade sheet is a matrix. It has rows with your name, columns with different assessments, and then I enter your grades into each of the little blocks. So the very formal definition, as it says here, it says a rectangular array of numbers made up of rows and columns. Remember, some of my kids stress with like which one's the row and which one's the column. I always say think about the columns on a house. They go up and down. So the columns go up and down and the rows go across. It says an M by N matrix. That's how we describe the size of the matrix. The first number is the rows, represents the rows, and the second number represents the columns. So an M by N matrix would have M rows and N columns. This description here, M by N, is what's called the dimension, or some people refer to it as the order of the matrix. I typically use the word dimension. Another way to think of that, I used to say RC for RC Cola, but many of you probably have no clue what that is. So the other one is matrices are really cool. So another lovely Miss Shop bad joke for you. And again, this first few slides were just mainly going through a lot of vocabulary because this is something new for you. So I talked about a matrix being a rectangular array of numbers. So we know that the rectangle, the length and the width do not have to be the same, but you can have what is actually called a square matrix, and that's where just the rows and columns are exactly the same. So your M and your N would be equal. So my question is, why do we have matrices? How do they help us? One of the big things that we use them for in mathematics is to help us solve systems of equations. And again, I've already said it's a way to organize your data, but for our purposes in today's lesson is we're going to use them to eventually solve systems of linear equations. We will only be looking at the inverse method. If we were in the classroom together, I would have shown you one other method, but since not everyone has access to a graphing calculator, I'm just going to look at the inverse method because I'm able to use Desmos to show you how to do that. So all of these numbers that are in a matrix, they're called the elements or the entries. And we have a way to describe them. And so for instance, in this example, we're talking about element and it has a subscript of a 3 and a 2. And so what that's asking us for is to find the element that is in the third row and the second column. So as I stated earlier, the rows are going to go across and the columns are going to go down. And so I'm going to use some highlighters here. So this would be our third row. And then we would want our second column. So this would be our second column. And so the answer to this problem is this one. So it's in the third row and the second column. So A sub 3, 2 is 1. I have seen in the past on some standardized tests where they will simply ask you like, what is element A sub 3, 2? And you would have to be able to identify it. So there's not any work really there. It's just looking at the matrix and finding the element that's in the third row and second column. For two matrices to be equal, they have to have the same dimension. So if you've got a 3 by 2, it can only equal another 3 by 2. And then all of those corresponding elements would have to be the same. We can have problems like this when we're solving. There could be some X's and Y's in one matrix and numbers in the other. And that will allow you to kind of set up some equations and solve for variables. You might see a few of those in the practice problems. All right, so on this page, it asks us to find the order of the following matrices. I'm definitely not going to find the order of all of these. Again, order is just another name for dimension. But we will look at a couple. If we look at U and V, so both of these are the same size. And so we want to do the row by the column, and there are 2 rows and 1 column. If we look at W, there are 3 rows and 1 column. Letter H, which I think is the one I used on the previous example, there are 3 rows and 3 columns. And that would be the same for letter G. Let's look at C. For C, there are 2 rows and 3 columns. So hopefully that's enough. Again, you're always remembering it's row by column. Again, rows go across, columns go down. All right, adding and subtracting matrices is probably one of the easiest things to do. You're simply just going to match up each of the corresponding elements and either add them or subtract them. So again, not really anything to write down here. I think once you see an example, you'll realize, oh yeah, I don't really need to take any notes on this. All right, so we're going to add these two matrices. One thing to note is both of these matrices have the same dimension. We have a 2 by 3, 2 rows and 3 columns, and another 2 by 3. And that is required to be able to do matrix addition, and your answer will be a 2 by 3. So we will start with the upper left-hand corner, and we're going to take a -5, and we're going to add that to this -3. And so that will give us a -8. Moving across, we will take an 8, switch colors, take an 8 plus a -4, and 8 and -4 will give us a +4. Then we can take this -9 and add to 0, which will give us -9. Then we can move on to the second row. We have a 7 plus an 8. So that will give us 15. Then we can take the 0 and 6. which will give us 6. And then lastly, we can take our 12 plus our -5, and that will give us 7. Sorry, trying to make that a little bit darker so it'll show up. So again, pretty straightforward, easy to follow. All right, so this example is subtraction. Again, they're already color coordinated. So I'm going to go through this one really quick. So we've got purple and purple. So -2 minus 7 would give me -9. 0 minus a -8 would turn that into a +8. 3 minus 0 would be 0. And then I don't really have a brown color. I guess I'll just use black. 6 minus 4 then would give us 2. And so that's subtraction. The next one is pretty simple as well. It says when you multiply a matrix by a scalar, and again, a scalar is just a number, specifically a real number. It's just like the distributive property. So if you have a number out in front of a matrix, you just distribute that number to each of the elements in the matrix. So this one asks us to find 3A. So again, we are essentially going to multiply every element in that matrix by the number 3. So 3A. And again, I'm going to go ahead and do the row first. So if I do 3 times 2, that gives me 6. 3 times -7, -21. 3 times 0 is 0. And then continuing with row 2, 3 times 3, 3 times 8, 3 times 4. And the last row, 3 times 5, 3 times 9, and 3 times -6. And so again, scalar multiplication is just as easy as addition and subtraction. A couple more vocabulary words. There's something called a zero matrix. Again, these are just some specialty matrices that are helpful in identifying some of our properties. But a zero matrix is literally just a matrix that has all zeros for the elements. So every entry is a 0. Your zero matrix is called the additive identity. So this will do a little bit of a review of properties, which again tend to come up on some of your standardized tests. Remember, if you have a number, you can add 0 to it and you get the identical thing that you started with. So just like an additive identity for 5 is 0, we can have an additive identity for a matrix, and it's simply a matrix with just zeros as the entries. Another vocab is an additive inverse. So inverse, we think opposite. And so if I have a matrix and I add its additive inverse, that means all the signs of that second matrix would be the opposite. So then we add them together, we get the zero matrix. So again, an inverse, think the opposite. So an additive inverse. Again, just kind of more vocab and that you may run into. So matrix multiplication, this is where it gets a little bit harder. So it says to multiply two matrices, the number of columns of the first matrix must be equal to the number of rows of the second matrix. And I have a graphic on the next slide to show you that. Hopefully will make that make a little bit more sense. I did make a note here that matrix multiplication is not commutative. And so like, for instance, we know that 3 times 4 is 12, and also 4 times 3 is also 12. But we cannot switch around matrix multiplication. Like if I multiply matrix A times matrix B, I would get a different answer if I was even able to multiply matrix B times matrix A. So be careful and make sure that you are following the order that's listed in the problem. So here's the graphic that I was referring to. So we have two matrices, matrix A and matrix B. Matrix A is a 3 by 4 matrix. Matrix B is a 4 by 1 matrix. and we said that the columns of the first matrix has to equal the rows of the second matrix, and in this case it does. And then what that tells you then is that your dimensions of your answer will be these outside numbers. So my dimensions of my answer matrix, it's going to be a 3 by 1. But again, those middle ones have to match up. They have to be equal. And if they're not equal, then we would not be able to multiply these matrices. And again, we'll work through an example and I'll show you how this works. So here I have two matrices, matrix A and matrix B, and it asked me to find AB. So let's first take a look at matrix A. Matrix A has 2 rows and 3 columns, so it's a 2 by 3. Matrix B has 3 rows and 2 columns. And again, we're supposed to follow the order of A times B, so we have to see, do the number of columns of the first matrix equal the number of rows of the second matrix? And they do. So we know that we can multiply these two matrices, and now we know the answer of when we multiply them, our dimensions will be a 2 by 2 matrix. So I know it's going to be a 2 by 2. Now, the way that we actually multiply these matrices is kind of difficult. Again, I wish we were together, but please, please, please reach out to me if you have questions. I'll do my best to kind of show you every little step and use the highlighters as much as I can. I may have to erase some as we go. So we talked about how matrices are defined to be the number of rows times the number of columns, and we kind of use that same idea when we're multiplying. So we're going to start off and we are going to multiply the row of the first matrix by the column of the second matrix. And so if you notice, we're multiplying row 1 times column 1. So my answer will go in the spot row 1, column 1. So I already know this is going to be a 2 by 2. I'm going to write this kind of large. And as you move across the row, you have to move down the column. So we're going to take the 1, and then we're going to multiply it by the 3. So the first element in the row times the first element in the column. And then we're going to add the product of the second term of the row times the second term of the column. And then lastly, we will have our last element of the row times the last element of the column. So again, kind of crazy. Now I am going to go ahead and multiply that row times our second column. So I'm still doing row 1 times column 2. So I'm going to erase this one. And now we're going to multiply by column 2. So we would have 1 times 1 then we would take 2 times 4, and lastly, negative 3 times 5. All right, so we've taken row 1 times column 1 and row 1 times column 2, and that filled in the first row. Now I'm going to erase my highlights for both of these. And now we're going to move on to row 2. So we're going to take row 2, and we're going to multiply it by column 1. So again, we keep moving. We're going to take the 4 times the 3 plus 0 times 2 plus negative 2 times negative 1. And then we'll do the same thing. We'll take row 2 and we'll multiply it by column 2, and that will fill in our final spot in our matrix. So 4 times 1 plus 0 times 4 plus -2 times 5. And then we just need to simplify these. So we'd have 3 plus 4, which is 7, plus 3, which would give us 10. I'll go ahead and go straight down the column. 4 times 3 would be 12. 0 times anything is 0. And then that would give us a +2, so that's 14. Moving over to the second column, we would have 1, 8. And so 1 plus 8 would give us 9. And then we would have plus -15. So I believe that's -6. And then that last spot, 4, we're going to get a 0 there in the middle. That would give us a -10. So 4 minus 10 would also give us another -6. And that is matrix multiplication. So just remember row times column. The rows of the first matrix times the column of the second matrix. You're multiplying the entries and then adding their products. Again, there are more examples in your textbook, or also I'm sure there's plenty of YouTube videos if you want to see more examples. All right, this is another one of those special matrices. We talked about the additive identity and the additive inverse. This is what is called the identity matrix. Again, something important here is the identity matrix has to be square. Okay, so it has to have the same number of rows and columns. And if you notice, it says there are ones on the main diagonal. So we can see that here. We have ones here on this main diagonal. This one says I sub 2. That represents a square matrix with 2 rows and 2 columns. Whereas the second one says I sub 5. So there are 5 rows and 5 columns. But they both have ones on that main diagonal from the upper left to the lower right and zeros everywhere else. Again, if we were in the classroom together, I would show you more what you would do using what's called reduced row echelon form that can be used in solving matrices. Back in the day, when I had to do this in class, I did not have a graphing calculator. Now there's like a couple buttons you push on your calculator and it does all the work for you. So, but come see me next year. I'll teach you how to do it. So when we think about identity, it kind of means think identity identical. And so what happens if you take a matrix and you multiply it by its identity, nothing's going to change. It's going to look exactly the same. And so that's the example that's kind of shown here. Again, they both have to be the same size. So their dimensions have to be the same. And since an identity matrix has to be square, obviously our other matrix also has to be square. In this one, it would not matter. If we wanted to, we could multiply A, B, C, D by our identity matrix. So we could reverse that order on this one. This is a very special case where it does not matter the order, and it's only because we are multiplying by the identity matrix. But I didn't want anybody to think that identity had to be listed first. It could be listed second. All right, the determinant of a square matrix. Notice this is of a square matrix. We can only find determinants if the matrix is square. So the kind of simple, easy one to do by hand is a 2 by 2 matrix. And the DET that you see there in the example stands for determinant. And this is also an operation that you will see on both your graphing calculators. You can also find this in Desmos for those of you that don't have a graphing calculator at home. But what it tells us here, it says we take the product of the main diagonal. And again, we refer to main diagonal. So we're doing this main diagonal of AD. So we're multiplying those together. And then we subtract the product of the other diagonal. And then they just showed you an example there with numbers. So we do 8 times 2 minus 4 times 3. So it's product minus other product. But again, it always has to be the main diagonal first, minus the other diagonal. So in this example, the determinant was equal to 4. So this one is pretty crazy. When we get to a 3 by 3 matrix, there's lots of different ways to do this. This is kind of what I think is the simplest way if you have to find the determinant by hand. And so I'll kind of try to describe to you what we've done here. And then I will work an example for us. So we have our matrix on the left, and those bars that kind of look like absolute value bars, that when you see those, that means find the determinant. So if it doesn't have the little DET out front and it just has the absolute value bars, you have to think, oh, that means find the determinant. And the way you do this for the 3 by 3, if you notice this first half of this matrix over here, again, I'm going to put some highlights on here and then I'll erase them, but this is just the same as our original matrix. But then what you notice is that all we did was we rewrote that matrix down again right beside it. So it's kind of like you write the matrix down twice. Then we look at the diagonals. And so we start, again, I'm going to clear this off and so we can kind of see it as we go. We start in this upper left-hand corner and we multiply the numbers along this diagonal. And that's a positive value. Then we move across and we multiply the numbers on this diagonal. And we add that. Moving forward, this third diagonal. And we add that. And then notice we can't go any further. So now we start working back in the other direction. But when we work backwards, we then subtract. And then again, just continuing to work your way. So we subtract, and again, I'll clear off all this color in just a second. And then lastly, how about green? So going forward, we add, going back, we subtract. And I think that purple is kind of hard to read. Again, you can rewind the video and go back if you need to see that. All right, so here is one that has been done for us already. We have this matrix D. Again, we see what looks like the absolute value bars. So that means find the determinant. And I've already shown you that the answer is negative 141. So we're going to start off writing all this out. So I'm going to show you how it works without letters because I know letters are kind of confusing just to look at. So first thing I do is I write down the matrix. So 2, negative 3, 8, negative 1, 4, negative 7, 6, negative 5, negative 9. Then I write that matrix down again. 2, negative 3, 8, negative 1, 4, negative 7, and 6, negative 5, negative 9. Then up above, just to remind myself, I'm going to put in those plus signs for the first 3 and the minus signs for the second 3. And then I'm going to try to be very careful with my marking so it doesn't get too terribly messy. We will start with this first row, and I think I'll just stick with yellow. So we start here. So we're going to take 2 times 4 times 9, and that would give me negative 72. And then for the second one, we're going to take negative 1 times negative 5 times 8, and that would give me 40. Then the third diagonal, 6 times negative 3 times negative 7, would give me 126. And again, we can't go any further. There's not another diagonal. So now we're ready to work back the other way. So I'm going to switch here for my highlighter and use an orange for this one. So we're going to work back this way. And remember, we are subtracting this time. So I'm going to indicate that here. So it's minus, and if I take 6 times 4 times 8, that will give me 70. And I'm going to put it in parentheses just to emphasize that we're subtracting. So once again, we're going to subtract. If I have -1 times -3 times -9, I believe that gives us -27. And then lastly, 2 times -5 times -7. Is a -192. And then if we stick all that in our calculator and combine our like terms, that will give us a -141. Guys, my apologies. I just realized that I put these numbers in the wrong spot. I was saying them and looking at my stuff I had on my paper, so my apologies. I had switched those two numbers. 7 times 5, -7 times -5 was gives 35, 35 times 2, so that was our actual 70. And then when I do the 6 times 4 times 8, that's where we came up with the 192. So sorry about that. It's kind of hard to do this remote. And then again, we'll still come up with the same answer. I had just listed those in the wrong spot. We do end up with that -141. All right, hopefully I didn't make any more mistakes. So that's how you find the determinant of a 3 by 3. Again, a very tedious process, very time consuming, not super hard. It just takes some work. So we talked about addition, subtraction, we multiplied by a scalar, then we multiplied matrices. And so you're probably thinking, okay, now it's time to divide. But matrix division is not defined. But you can multiply a matrix by its inverse. This involves using determinants. And so that kind of, hopefully you can think back to what we talked about earlier. You can only find the determinant of a square matrix. So if the matrix is not square, you will not be able to do this. So we will look at how to find the inverse of a 2 by 2 matrix. Higher than a 2 by 2, it becomes very complex. So we're only going to look at a 2 by 2 by hand. So the little -1, you may think that's like our inverse notation. We studied functions. So to find the inverse of a matrix, and we have our standard 2 by 2 matrix, A, B, C, D. What you do is you take 1 over the determinant, and so you may or may not realize that this right here is the determinant of the matrix. So AD minus BC. And then what we've done with the matrix is we have switched the main diagonal. So this diagonal that was AD, hang on, let me switch colors here. So this diagonal that was AD has become DA. And then what we do with the other diagonal, this diagonal was BC, and we're going to make both of those the opposite sign. So you switch the main diagonal and change the signs of the other diagonal. And again, you're multiplying that by 1 over the determinant. So like 1/5 could be the number out in front. It just depends on whatever the determinant of the matrix is. And so it turns into a scalar times this new matrix. So when you multiply a matrix by its inverse, you get the identity matrix. So when we talked about inverse functions, maybe kind of relate this to composition of functions. When you would plug a function into its inverse, they would kind of undo each other, and we would simply get x. So here, when you multiply a matrix by its inverse, you end up with that identity matrix. Again, the identity matrix is the one that has the 1s on the main diagonal and 0s everywhere else. But I have some good news for you. you can use Desmos for matrices. You cannot do this like this. The operations for matrices are not in the regular Desmos graphing calculator. So you can just type in desmos.com/matrix. And then you can just kind of play around with it, do some exploring. I actually just Googled it, went on YouTube, and the first video that came up is pretty good. It goes just through the basics. There's a second video that comes up that's good for section 7.3. Again, I didn't put links or anything since this is just in a video, but if anybody needs me to send links, just shoot me an email and I'll be happy to do that. But I have faith in you guys that you can find them. Also, you can use your graphing calculator for matrices. So I just try to take some screenshots here, and I'll try to kind of walk you through this a little bit. So this is pretty small. So to find matrices, so to access that, you're going to have to hit the second and the X to the -1 button. So again, kind of hard to see here, but it's that you're going to press the second button and then that X to the -1, and that will pull up this screen that we see on our calculator here. So it has names, it has math, and it has edit. So if you scroll over to the right to edit, then that will allow you to type in a matrix. And if you see here, I had decided I was going to make a 2x3 matrix. And as soon as I typed in a 2x3, it actually made a matrix for me. I can see that there are 2 rows and 3 columns. And then you would just enter the numbers. As you enter these, if you enter the first element, then you press enter, it will take you to the second element and so forth until you've entered all 6. Here's another example. I put in a 2x2 matrix, my favorite 1, 2, 3, 4. Also showing you that that middle option is math, and number 1 there under math is DET, so that's finding the determinant. Again, I had started putting in matrix A, which is a 2x3, then I entered matrix B, which was a 2x2. So then I found the determinant, and then the way you pull up the name of the matrix. So in order to get this B right here, you have to go under names and choose B. And you can just click the number 2, or you can scroll down and press enter. And then press enter again, and it will give you the determinant of that matrix. Again, a 2x2 is pretty easy to do in your head. Reminder there, we take the main diagonal, so that would be 1 times 4 minus the other diagonal, which is 2 times 3. And so we get 4 minus 6, which is, ta-da, -2. But again, showing you here, 2x2s, it's to me much quicker just to do it in my head. For 3x3, it might be worth putting that matrix into my calculator to find the determinant, because it is very time consuming, as you saw before. All right, we're going to move on now to 7.3. We're going to look at solving systems of equations using matrices. There is a ton of information on pages 592 through 601. Again, I'm just taking a brief little snippet from this section. So if you look in there and think, wow, she didn't teach me all this, you're exactly right. All I'm going to focus on is solving using inverse matrices. So you may remember way back in Math 1, you learn how to solve a system of equations. We go through and we learn how to do that graphically, also using substitution and elimination. But again, I'm going to show you, hey, there's even another way, and it involves using matrices. Back in the day, probably I think when I first started teaching at Millbrook, and when I taught at previous schools, matrices was actually a part of the Algebra 1/Math 1 curriculum. So like I said, it kind of keeps getting moved around when they rewrite the standards, but it's coming back, but now it is a 4th level math topic. So we're just going to do an example. It says, consider the following system: 3x minus 2y equals 0 and -x plus y equals 5. It says we can write the system as a matrix equation, ax equals b, where a is the coefficient matrix, x is the variable matrix, and b is the constant matrix. So I'm going to do that for you now. So we're going to start with matrix A, and matrix A is just the coefficients. And so we've got a 3. And then we look at this negative x. Remember, there's really a 1 right there. So I'm going to put a negative 1. And then the second column, the coefficient of the y is a negative 2. And then we have a 1. So again, this first column is representing our x's, our coefficients of the x's. The second column is the coefficient of the y's. And then we're going to multiply this by our variable matrix, which is x's and y's. And then we'll equal our constant matrix, which is the 0 and the 5. I'm going to erase that x and the y up there so it doesn't confuse you. So that is how we take a system of equations and represent it using matrices. So it says now we need to solve that equation for, and that's a big X, so that's matrix X. So we're trying to figure out what X and Y are. And normally we would just say, oh, you divide both sides and boom, now you have your variable. But since we're doing matrices and we know that matrix division's not defined, we have to multiply both sides by the inverse to get the big X, so the variable matrix by itself. And so I have a question for you. Does order matter? Do we find B times A inverse or A inverse times B? Well, if we think about matrix A from the previous page, matrix A was a 2 by 2 matrix, which means that A inverse will also be a 2 by 2 matrix. Matrix B was a 2 by 1 matrix. So when I'm trying to decide if I'm going to multiply A inverse times B or B times A inverse, the only way it's going to work is if we multiply A inverse times B. Because if you remember, the columns of the first matrix has to equal the rows of the second matrix. And if we tried to do B times A inverse, this one, it's not possible. So I'm going to do this one by hand, again, because it's pretty simple. And hopefully I've left myself enough room here. So if you remember, I think I'm going to squeeze it in up here. Not sure if you wrote it down from the last example, but our matrix A was the matrix 3, -1, -2, and 1. And matrix B was 0, 5. So that'll be helpful for us to go back and look at these. So I first need to figure out, well, what is A inverse? So to find A inverse, if you recall, it's 1 over the determinant. So we take the main diagonal. So 3 times 1 would give me 3 minus the other diagonal. -2 times -1 would give me 2. And then we switch the main diagonal. So we've got a 1 here and a 3 here. And then we do the opposite of the other diagonal. So we're changing the sign so it becomes a +2 and a +1. And since 3 minus 2 is 1, we have a scalar of 1. So that matrix is not going to change. It is just 1, 1, 2, 3. And so now we need to find matrix X. So our variable matrix. And we said we're going to do A inverse times B. We just found A inverse was 1, 1, 2, 3. And we multiply that by our constant matrix, which was 0, 5. Just to remind you again, this one is a 2 by 2. This matrix is a 2 by 1. These match. Therefore, our answer will be a 2 by 1 matrix. And so if we take 1 times 0 is going to give us 0, 2 times 5 is going to give us 10, so that's 10. And then the second row, 1 times 0 is 0, 3 times 5 is 15. And so that is our variable matrix. So x is 10 and y is 15. We could write that even as an ordered pair, 10, 15. So again, this is pretty simple for solving a system of equations that has 2 variables, but when we work with 3 variables, 4 variables, something like that, this gets much more difficult, and you don't want to solve by graphing or substitution or elimination. So matrices make those 3-dimensional, 4-dimensional system problems much more manageable. So, for instance, here, it says solve the following system using matrices, and it says you can use your calculator. Again, you will decide if you have your own graphing calculator at home or Desmos. So in order to do this, I'm going to write out our matrices that we would need. First, maybe let's look at our equation. So we want to find matrix A, and so that's our coefficient matrix. So 3, 1, -1 are your coefficients of x. -3, -3, and 3 are your coefficients for y. 6, 10, and -5 are your coefficients for z. If you have a variable that's not listed, if there's not one, that means you have 0 of them. So if anytime you're missing a variable, an equation, you'll just use a 0 for that coefficient. Again, this time we would be multiplying by x, y, z would be our variable matrix. And then that should equal our constant matrix, which is 20, 40, 30. So this is matrix A times x equals b. And so to solve for x, we have to take A inverse and multiply it by matrix B. And so at this time, I would like for you to either use your graphing calculator or Desmos. Type in matrix A, type in matrix B, do A inverse, again in Desmos. I didn't do screenshots of it for you, but in Desmos you can see there's a little -1 button to find an inverse, and you multiply that matrix B, or you can use your graphing calculator. So when you go ahead and press pause now in the video, type those in, and then when you're ready to check your answer, press play again. Okay, if you have not done so, again, get ready to write the answer down. So press pause if you're not ready for it. So when you multiply matrix, or the inverse of matrix A times matrix B, you'll get 18, 39.3 repeating, and 14. So again, if we want to write that, this would not be an ordered pair, it will be an ordered triple. You would get 18, 39.3, and 14. So that is your X, your Y, and your Z. Again, it would not be fun to have to do this using the elimination method, and I can't even imagine trying to use substitution. So definitely matrices is the way to go when you have 3-dimensional system of equations. So that wraps up this week. Again, you have practice problems from 7.2 and 7.3. Again, you're welcome to use your calculator for these, keeping in mind that sometimes it takes more time to type them in the calculator than just doing them by hand, but definitely anything with 3 variables, I would go straight to my calculator. So 7.2 and 7.3, and then you have your matrices quiz in Canvas. Again, I believe it is 8 questions. Hope everybody had a great Memorial Day weekend, staying safe, and I will see you next week. Take care. Bye.